Hi, this isn't exactly going to be a Fundamentals Friday as you probably expected, but I was just ran across this issue that I thought I'd check out today, so I thought, oh, why not turn on the camera and let you have a look at it as well. So I guess it is kind of fundamental. It, comes down to looking at data sheets and measuring things, so, it's a fundamental problem that we all have to deal with eventually. Anyway, what I've got is this Analog Devices AD8628. It's a really schmicko, as it says, zero drift, single supply, rail to rail operational amplifier, and it's actually a chopper amplifier, as I've done a video on. If you haven't seen a video on chopper amps, I will link that right here down below, so click on that and watch that if you want to. It's one of my much older videos. Anyway, pretty much one of the best zero drift, low offset voltage operational amplifiers you can get on the market. And yes, it's got that chopper configuration to get a very low offset voltage. Check out some of the banner specs here. It claims to be the lowest auto zero amplifier noise of presumably any amplifier on the market. Awesome, super low offset voltage, only 1 microvolts. That will be a typical voltage, as we'll see, not a maximum voltage. And input offset drift, it's essentially zero. Look at it, it's 2.002 microvolts per degree C, or 2 nanovolts per degree C. So once it's got that 1 micro, let's say this particular chip, the one you've got, has 1 microvolt input offset voltage, then that value of 1 microvolts is only going to drift by 2 nanovolts per degree C. Incredibly stable chip. Fantastic. Well, that's one of the reasons I'm using it here. Now, it's got rail-to-rail input and output swing. Fantastic. So you can take the input down to 0 volts, or you can take it all the way up to the supply voltage. And same with the output as well. So you can utilize the maximum output range. Single supply operation, it actually goes down to 2.5 volts or thereabouts. So perfect for my application. High gain, yeah, kind of 130 dB common mode rejection ratio, all that sort of stuff. Low input bias current, 100 picoamps, good enough for my application. Low power supply current, it's under a milliamp, good enough. Overload recovery time, it's not bad for a chopper amp. No external components, it's all internal. All the chopper circuitry and stuff all runs internally, and the oscillator is all internal and all that sort of stuff, as is typical with chopper amps these days, and it's qualified for automotive applications. Whoop-de-doo. But anyway, I built this, I used this chip, and I discovered a little weird problem, well, an issue with it that I wasn't really expecting, and it took me a little bit of a while to figure out what was actually going on with this thing. I actually mentioned on the Amp Hour a couple of episodes ago, actually. If you want to listen to that, here's a brief description of it on there. And anyway, I thought I've figured out what the issue is, but I thought I would double check it by actually building it up from scratch again and actually verifying that it's the case in various scenarios. So that's exactly what I'm going to do today. So I thought I'd turn on the camera and give you a look at it. I was slightly off on the supply voltage there. It's actually 2.7 volts to 5 volts single supply operation. Now, as with all op amps, they don't care whether or not you're using them from a dual supply or a split supply, subject to input and output, common mode range and output range and stuff like that. So it can actually operate from plus minus 1.35 volts. That's like practically, plus minus a single cell, single alkaline cell, to plus minus 2.5 volt dual supply. So an ideal op amp to be operating from a coin cell or something like that. If you've got a strain gauge or something that's operating from battery, fantastic device. And apparently the chip combines the benefits previous only found in expensive or auto-zeroing or chopper stabilized amplifiers. And yes, there can be differences there, which I won't go into. As you can see, the noise is pretty low too, 0.5 microvolts peak to peak, from 0 hertz up to 10 hertz. So awesome device. It's pretty hard to, I think you'll be pretty hard pressed to get a better device than this. There are lower ones in terms of offset voltage, but not sort of like combined in terms of offset voltage plus noise plus drift. So, one of the best op amps on the market. Now before we have a look at the problem, I'll just look at some of the specs to give you some background on the issue here. Now these are the electrical characteristics at a supply voltage of 5 volts, i.e. plus minus 2.5 volts, which was pretty close to what I was working at. I was actually working off 3 fresh alkaline cells, so it was like a 4.5 volt supply. Now the input offset voltage is the thing that we're concerned with today. Here are the typical figures for it, okay? Typical figure at 25 degrees C, by the way, with the common mode voltage, by the way, smack in the middle there, which was how I was basically operating with a split supply. Now, the offset voltage here, the input offset voltage, typically 1 microvolt, and that's the banner spec. But of course, you don't take the, you can't always just take the banner spec. You've got to look at the maximum value as well. In this case, 5 microvolts maximum. And if you want to take the full temperature range into account, which I don't have to, then it can be as bad as 10 microvolts. That's still pretty low, but it's order of magnitude worse than the headline spec they tell you on the front page. That's always a trap for young players with these data sheets. If you just read these front pages here, these headline specs up here, they don't give you all the detail. They're going to lie. It's basically marketing wank up here. Well, they're not going to lie, but they're not going to tell you the whole truth and nothing but the truth. This is where you have to look in the electrical specifications here. So this is what we're really concerned with. Input bias current doesn't really concern me, really, and or the rejection ratio and all that sort of stuff doesn't really matter. And of course the drift is so low, 2 nanovolts per degree C, that, geez, you don't even have to worry about it. But not that it would come into play anyway, even if it was high, because the lab here is essentially a fixed temperature. It's only going to vary with the aircon on by, plus minus half a degree, a degree or something like that. Now, this looks like an identical page, but it's not. It's actually the next page over, the electrical characteristics now for a supply voltage of 2.7 volts. We had 5 volts before, and once again, common mode voltage 1.35 volts, smack in the middle, and we've basically got exactly the same numbers here. 1 microvolt typical for the input offset voltage, which is the issue that I had. Now, if you scroll further through the data sheet, you come to, well, the first thing you come to, because they're quite proud of it, is the input offset voltage here on the x-axis. Here we go. It's sort of 0 is sort of there, right about there. And, this is at 2.7 volts. Let's look at the 5 volt one. There's our 0, right in the center there. And our input offset voltage can be plus minus that with a common mode voltage of 2.5 volts. So smack in the middle, and you get that characteristic bell curve kind of shape in your values. And these are the number of amplifiers. So they actually measured, 10, 20, like 80 amplifiers. So they measured a couple of hundred amplifiers here, and this is the response that they actually got. And yet it's always typical. It's going to be, when you get manufacturing process variations like this, you're typically going to get, given enough devices, that bell-shaped characteristic response, that bell curve as they call it. So let's, here most of them are centered around 0, and most of them, the bulk, are going to be within plus minus 0.5 microvolts. So it's, around about that 1 microvolt typical figure. Not bad. See, here's the majority of them. Oh, there's one microvolt from plus minus 1. I guess they only give 1 microvolt typical. They don't say that's plus minus. Anyway, even at 2.7 volts down here, so when you vary the supply voltage, which is what we're going to look at later, then you'll notice that, yeah, it's been shifted up a bit. There's our 0 point, but still, it's very low. None of them are getting anywhere near that maximum figure of 5 microvolts, right? So we expect, if we bought some of these chips, odds are, not guaranteed, of course, but you can be pretty darn certain that's going to fall within there. It's going to be like, at least under 2 microvolts, for example. There's a couple of outliers out here, for example, but gee, you expect it to be pretty close to that typical value of 1 microvolts. And I found, when I built this thing up, that wasn't the case. I was getting up to 5 microvolts offset. Let's go to the breadboard. But before we do that, let's take a look at the circuit which we're looking at here. It's the AD8628 op-amp. It's a single op-amp SO8 package, and I've got it set for a non-inverting gain of 100 here, or it's actually 101, using 1K and 100K, who cares? Near enough to 100, right? So then we're going to have an input offset voltage here, that 1 microvolts typical. And of course that input offset voltage there is going to get multiplied by the gain of your op-amp. That's how it works. It's not just for this op-amp, it's for all op-amps. It's going to do that. So let's say that this particular device that we have under test has 1 microvolt there. We expect 100 microvolts on the output here, or 0.1 millivolts. So we'll build it up, and we'll see if we get it. Of course, I've just got a couple of bypass caps on here. I've got a split supply. In this case, it can go anywhere from from 2.7 total up to 5 volts. Now, what I've done is gone and actually assembled this chip on one of my microcurrent boards here, because it has the same configuration, just allows me to easily do that. I removed all other circuitry on there, the rail splitter and all that sort of stuff. So it's powered from my external bench supply, positive supply, negative supply, and my and there's the ground, and that's my output. Now I've got my output voltage on here, and I've got my supply rail here, so it's 5 volts total across here, so split is plus minus 2.5 volts. So, you know, the maximum range that this thing can operate at. And if you remember, look at our spec here. Typical figure of 1 microvolt offset voltage at and a maximum of 5. So we'd expect that typical value, remember, based on that bell curve. So I've got a times 101 gain in here, near enough to 100. And look what we're getting on the output. We're getting 300 odd microvolts, or thereabouts, 0.3 millivolts. If you divide that by 100, that's 3 microvolts offset voltage. And sure, okay, it's within spec. You know, you think, okay, not a problem, so it's within spec. Okay, fair enough, nothing wrong with the chip. Okay, and that's what I thought the first time. Oh, look, I've just got a bad one. You know, but no, I replaced it. Now I replaced it again, I replaced it again. And no, all of them had around about this same 300 odd microvolts offset voltage. And I was scratching my head for ages trying to figure out what it actually was. And yes, I've deliberately shown this ground point down here as a star point so that everything is referenced to that. The input voltage there is referenced directly to there, the output voltage is referenced to there, and that's really going to matter if you've got any significant current flowing through those traces, but we don't with our high impedance, you know, 10 mega ohm input multimeter and stuff like that. So the star grounding doesn't really matter in this particular scenario, but I've just drawn it there for completeness. And yes, that input voltage pin 3, that's that little blue wire looping across there, that's shorted out directly to there. So, you know, our input, so we're amplifying our VOS, our input offset voltage, by 100 basically, and that's what we're getting, regardless of what chip I put in here. And trust me, I've tested quite a few of them. So now I've got it down to just this scenario here with the split supply. So what's going on? Is the typical figure a load of bullshit? Well, I tried all sorts of things, hacking and slashing my circuit, you know. I've got something, there's something weird going on in the layout, there's something wrong with my power supply, yada yada. I was pouring through the data sheets and everything, until I just thought, I wonder what happens if I take the supply voltage down. And here we go. Let me wind down the wick, right? And you remember, back here, here's the 5 volt one. You remember, there it is, 5 volts, typical figure, 1 microvolt, 5 microvolts, 2 points the minimum, 2.7 volts, typical figures remain the same. So you don't expect that offset voltage to change at all, right? Well, let's look what happens when we wind this power supply down. Look at that. It's dropping, it's dropping, it's dropping. Look. Magic, folks. Look what happens when we get down to 2.7 volts. It's bordering on, you know, it's zero. It's like, you know, it's very low. In fact, it actually went negative, right? And you'll see it, we wind it up a bit, it goes positive again. So we can actually almost null that out. You know, there it is at, you know, 3 volts. and that's going to vary with chip. Why is this thing changing with the supply voltage? According to the spec sheet, it shouldn't. The typical figure should be the same, and it's not just this one chip. I've tried this on many different devices, and it's exactly the same. Now, the thing I actually wanted to try today, because I've already tried this in my real circuit, and yeah, I've verified that this is the case. So what I actually wanted to try today before I turn the camera on is, does this do it based on a single supply? Because I've got a split supply at the moment, and effectively this point here, this ground point, the reference point, is sitting smack in the middle of that supply voltage range, right? So what I want to do is power this from a single supply. So effectively, I'm just going to now short out this ground point to this negative point and only power it from a single supply. So I got to, I won't do this live. I don't want to blow up my chip if I goof it up. So let me reconfigure it. All right, I've reconfigured it now. So essentially, I've just shorted out this point, that ground point, to the negative rail, and I'm now running it from a single supply. And here it is, 2.7 volts minimum supply, and we're getting about 73 microvolts out, or about, divided by 100, 0.7 microvolts offset voltage, around that typical figure we expect. Now let's wind it up, and I haven't tried this. Let's see if it increases. It is. It's going up. It's going up. Not by a huge amount, though. Look at that. So we can go up to a maximum supply voltage of 5 volts. So there you go. It's the fact that, don't want to go over that. That is its maximum supply. Its absolute maximum is 6, but I won't take it there. There you go. It hasn't gone up much at all. So it's the fact that we're actually running this split supply is the thing that causes the issue here. When you actually power it from just a single supply, you don't get this offset issue at all. Strange. I don't know why that's the case. And just to show you that it's not that chip, I've actually soldered another one onto one of my microcurrent boards, so this doesn't have the Maxim chip in it anymore. It's got the Analog Devices chip in it, and there we go. Let's take it up to 5 volts. There we go. This one's actually even higher. This one's 400 microvolts, or 4 microvolts offset voltage, and once again it varies with that supply rail. Check it out, down to 2.7. There it is, where it goes down to incredibly low. Unbelievable. And just to show that it's different with the Maxim chip, I've got one of my original microcurrent boards with the Max 4239 in there, and it's let's take it up and look, even it up at 5 volts. There you go. No, it's incredibly low, because this one's typically 0.1 microvolts offset voltage, so it's actually lower than the Analog Devices one, but its drift and its noise is higher and its bandwidth is lower and all that sort of stuff. But yeah, so there you go. Not a problem on the Maxim chip. Now, just for another comparison, I've got another low drift Auto Zero chopper amp here. It's the microchip MCP6V01. It's not quite as good, but it's of either of the devices, but it's not bad at all. It's typical, or its max value is plus minus 2 microvolts offset voltage, and once again they've got a percentage of occurrences versus microvolts offset voltage there, and as you can see, you know, they pretty much the sample falls within that plus minus 1 microvolt, so we should expect less than 100 microvolts on the output, and there it is. That's exactly what we're getting. If I switch off my supply, of course, it just goes blah, and there we go. I switch my supply on, so it's jumping around a bit there, but it's close to 0. We're just getting some noise there. That's why actually this one goes down to 1.8 volts. Actually, let's see if this one varies with supply. There we go. There we go. Minus 350. So this one does vary. This one is rated from, look, it's here. Here it is, plus 1.8 volts to 5.5 volts. There you go. So that one on the low side there, but once it gets, there you go, once it gets sort of 2.1 volts there, but sort of at that 2.7 volts, which we were using before for the other ones as a reference, basically zero. So well within spec, of course. We're only talking, you know, 0.1, 0.2 microvolts or something like that, offset voltage. And we wind the wick up, and no, it's not really increasing, so it's doing the same as the Maxim chip pretty much. It's offset voltage, oh no, hang on. No, there we go. Pretty consistent over the voltage range. I mean, you know, to get rid of that noise, we could probably like turn on some averaging or something like that. This microchip one's performing the same as the Maxim one, so it looks like the Analog Devices one, there's something peculiar with that. So I've put my Analog Devices one back in here, and of course this is not using the split bench supply anymore. It's utilizing the split supply on my microcurrent here, but it doesn't seem to make any difference whether or not I use the split supply, the Opamp virtual ground split supply on here, or my bench supply, as you'd expect. Really, you wouldn't expect any difference, but there it is. I got the average mode on there. And down at 2.7 volts, it's, you know, it's very low, very respectable. But let's wind the wick up, and we can turn that off. Actually, I'll turn that off. Boom, there we go. We're getting our 400 microvolts. There we go. Yeah, that average would have taken some time to creep up there. But look at that. There you go. So there's something with that split supply. Unbelievable. But even going back to our original one here in single supply rail operation, it still does vary. So from 2.7, we're getting 0.54 microvolts offset voltage, and it does actually go up. I mean, you know, it practically doubles there. Whoops. Practically doubles over the operational supply voltage range. And just for fun, what I've done is I've actually desoldered these 0.1 microfarad bypass caps. I'm back to a split supply, plus minus, with the split ground here, and I've replaced that with a single cap between the positive and negative supply directly across the chip there. And let's have a look at what we get. We're getting about 200 microvolts or 2 microvolts offset voltage there at 5 volts. But if we wind that wick down, it drops significantly faster than what it did before. Look at that. Now at 4 volts, it's sort of, you know, at the level we expect, and it's gone a bit negative. Look at that. Isn't that interesting? By the way, that was a 330 nanofarad directly across there before. Now what I've done is just soldered the negative one back in there, and I'm just using that. I've got no bypass in the positive rail there. And 2.7, and up we go. Look at that. Look at that. And now it's significantly worse at that 5 volt rail there. Aha. And now I've soldered in the other cap, once again 100N, so I'm back to our original configuration, 100N, 100N bypass with a split supply, and this is what we're getting. That's a 2.7, and we're back to our original configuration basically. So there it is. There it is. It's got something to do with the bypass caps, and presumably the input, I don't know, something to do, well, you know, it's probably got something to do with the internal operation of the Auto Zero chopper amp inside this thing. You know, I don't know the exact configuration in there, so, you know, who knows, right? Only Analog Devices could tell us that. But there is a difference when we put in different value caps for the bypass in different configurations. So maybe it's got something to do with the input bias currents to the op amp, but why that matters when they're both effectively tied down to the same star point like this, gee, I don't know. So I'd love to give you an exact solution for this one, folks, but unfortunately I don't. That's as far as I've gotten, and really I'm rather perplexed. Maybe it is something incredibly simple, and it may turn out to be something embarrassingly simple, but I don't know. I just haven't been able to get to the bottom of this stupid thing, and it's got something to do with this particular Analog Devices one. The others don't actually show this issue at all. Both the Maxim and the microchip part don't show it. It's only this Analog Devices, and it's still an awesome chip, by the way. I'm still going to use it. This is just a really, you know, I'm going to put a regulator in there. The power supply is not going to vary anyway, so, you know, it's not going to be an issue. But when I first discovered this, I just thought, what the hell's going on there? It's rather interesting, so I thought I'd at least investigate it. So it's not a huge deal, but it's just interesting. So if anyone from Analog Devices is actually watching and can shed some light on this, please do. If you've got any better ideas yourself, leave it in the comments or on the EEVblog forum. And maybe it's got something to do with the patented, oh yes, there's the problem, they patented the damn thing, ping pong operation they call it. It's auto zero and chop-in at the same time in some unique patented configuration. I don't know, maybe it's got something to do with that, but it's really, really bizarre. And why those capacitor values and configurations make a difference, the bypass caps, I don't know. In theory, they shouldn't. Really, maybe it's you know, something to do with the just the input configuration of this chip and the chop-in nature and etc., the topology used in this particular Analog Devices one, because I don't seem to get it with the Maxim or the microchip part. I don't think I've ever seen anything like this before, and well, yeah, it could turn out to be embarrassingly simple. I don't know, and I'm probably just making a dick out of myself. But anyway, that's just some playing around with the input, measuring the input offset voltage. And by the way, if you're wondering, no, you can't just put your multimeter on there, and even if it's a 6.5 digit one, and measure your offset voltage on there. It's actually internal, generated internal inside the circuitry in there. So, you know, you could have a big blob of solder between those, and, you know, you're still going to get this input offset voltage. It's inherent in the design of all op amps, even these ultra low offset ones. In this case, you know, like the best on the market is, you know, 0.1 microvolts or something like that, which is the Maxim one, I think, anyway. Typical figure, but worst case. And yeah, so we learn a bit about worst case and bell curves and all sorts of jazz. So I hope you found that interesting. That's just me looking at a few little issues in input offset voltage. So hope you enjoyed that. And if you like, well, this really wasn't a Fundamentals Friday. Sorry, it was just me dicking around. But yeah, anyway, hopefully you found it interesting. And if you do like it, give it a thumbs up. Catch you next time.